truth tables, but before you obviously have to understand truth tables, you kind of have to know the propositional logics so that you can draw your truth tables. A proposition is basically a statement that has exactly one truth value, so it can either be true or false, where if you're doing computer systems, you only deal with binary, so you can either have 1 or 0, but for this case, we can also have true or false. An example would be 5 plus 2, that is equal to 7, so it's true, right? If I say to you, Johannesburg is in South Africa, that is also true, so the proposition is true. The statement has one truth value. If I say ice is made from eggs, the proposition is now false, so the statement is false. You can't have ice being made from eggs. That is false. However, if I say to you, come here, that is not a proposition, it's not a statement. It can be true and it can't be false. So even if I had a full stop like this, where one would say it's a statement, the proposition would not be there, right? So it's a statement, yes, but the proposition would not be there. So it can't be true and it can't be false. So when you obviously write if age is greater than or equal to 18 and has ID, that is now a propositional logic. Remember, logic has to do with your ands, your nots, and your, let's say, your or, your XOR, your NAND, and stuff like that. So that is logic. So propositional logic would be if your logic or your statement has a true or false. So I wrote here that's a propositional logic because the computer must determine whether age is greater than or equal to 18 and also has ID. So instead of obviously the computer having to do this, it would have variables to, or you can say, yeah, placeholders or to store in the data. For example, it would look at it as P and Q, right? So every time there's P, you know that this data is stored in, and for Q, this data is stored in. So if you do programming, you're going to learn about variables where you're storing in data instead of having to write long sentences. You would want to have variables instead. Here's another example I have. So let R be it is raining and G be I have an umbrella. So that would mean R and G is equal to it is raining, and because there's that operator, I have an umbrella. Now there's 5 main logic operators, namely you have your not, your and, your or, your implication, and your bio condition. So if something is like this, the symbol has a not like this, you read it as not P. If it has an upside down looking V, you would say and obviously when you're doing sets, you would have an upside down U or N, and that would be your and, right? But now that we're not doing sets, we're working with propositional logic, so we're working with statements instead of sets or elements, so you would want to use these kinds of operators instead. So the or is a V or up looking V, so you read it as P or Q, and implication would be an arrow facing that implication. So P, if P is true, then Q would be whatever, right? And P and the bio condition would basically be P is true if and only if Q is this condition. So they have to match conditions. With your not operator, you would say a unary operation in computer systems. So basically there's two cases. So you either have this case or you have that case, and this would be your truth table. So unary means one input produces one output. So we have one input producing one output, right, for each row. So for the first case, if you have A being 1, not A would be 0. So not A would be the complement of A, so anything outside A, and that is 0. If A was 0, anything outside A is not A, so it would be the 1. And yeah, for your Venn diagrams, that's how you can think of it. And then we have the binary operations, which would be your and, your or, your I think implication and bio condition as well. So those are your binary operations. So binary means 2 inputs produce 1 output. There's 4 cases in each. So case number 1 for the and, we're going to start with the and then the or. So if you have A and B would be 1. So we're not looking at anything outside A and B because we're comparing A and B. Okay, so that if A is 1 and B is 1, A and B would be 1. Case number 2 would be if A is 1 and B is 0, that means you don't have anything inclusive and the system is false. So remember, we compare 1 with true and 0 with false. So if A is 1 and B is 0, yes, the system is false or the system is 0. But if A is 0 and B is 1, it's still not mutually inclusive. You can't have two different things happening at the same time. So you'd still say the system is off or system is false. So 0, 1 means 0. But if A and B are 0, so if the system is off in both states, that would mean off state. Let's do the OR. So as you can see, 2 inputs produce 1 output. And we're going to do the OR as well. So if you have A or B, so we're not looking outside the sample space. So we're not looking at anything that's happening here. We're looking inside A and or B, right? So A or B. So if A is 1 or B is 1, you get 1. Second case would be if A is 1 and B is 0, you're getting A or B. So the system is going to be, so if the system is true or the system is false, at least because it's true, you're going to get a true. If the system is off and on at the same time, or different times, then it's on. So it's either it's true or it's false. So because there's a true, that means it can be on. But if it's both off, then it's going to be off. Implication would mean you implying something and you're expecting something based on what you implied. So for example, if you say, if I study, I will pass. So you're implying that if you study, then you would pass. So if Q is true, then P has to be true, right? So for example, if P is true, if you study, then you pass. And that is true, obviously. So if you study, then you will pass. But if you study and you don't pass, so it means your implication was wrong. So you studied, but you didn't pass. So that would be off, right? So you studied and you didn't pass. That is off. And if you didn't study, for example, if you didn't study, then you will not pass. So that's another condition or implication. The implication is true then. So if you didn't study, then you will not pass, and that is true. However, if you didn't study and then you pass, that is true. Okay, let's do by condition. So basically, the example I want to give here is if I'm hungry, I will, if I'm, no, let's say I will cook only if and only if I'm hungry. I will cook if and only if I'm hungry. So basically, these two have to match. So I will cook if and only if I'm hungry. So if I'm hungry and I cook, that system is true. But if I'm not hungry and I cook, the system is false because I stated that I will only cook if I'm hungry. And if I'm hungry and I don't cook, the system is off. Sorry, off, because I stated that I will only cook if I'm hungry, but now I'm cooking and I'm not hungry, so the system is off. However, if I'm not hungry, then I'm not going to cook. The system would be on. So basically, you have to have two of the same truths to produce a truth value of true. It's not the same as the implication. So implying something is not saying if it happens like this, then I'm going to do this. You're just assuming that if you do something, then you're going to get a result, right? And so you don't know that. What you don't know is if your assumption is wrong, what is going to happen? You don't know that because you're just assuming that something is true. Hence the last statement here. So if you don't study, you don't know if you're going to pass or fail. So the system is still true. It can happen, so it's still true. And then from this, obviously they can ask you different types of questions. You can have your notes and stuff like that, and you'd have to draw a very huge truth table. So do practice your truth tables, and I think maybe I might post a video on that alone, but I just needed to, or for you guys to understand certain conditions and how they apply.